This presentation will introduce you to the power plant installed on the 737. First, we will look at the controls and indicators, followed by a discussion of the fuel system, oil system, and engine instruments. The 737 is powered by CFM 56-3 high bypass turbofan engines and one of the following thrust ratings. The CFM 56-3 turbofan engine has two mechanically independent rotor sections, N1 and N2. N1 consists of one large diameter fan and three booster stages driven by a four-stage turbine. N2 consists of 9 compressor stages driven by a single-stage turbine. Air entering the engine passes through the fan stage and is divided. Part of the air passes through the center of the engine for combustion. The remainder of the air is routed through a duct surrounding the engine to provide the major portion of the thrust. Reverse thrust is accomplished by left and right translating reverser sleeves on each engine, which allow fan discharge air to be deflected forward. The accessory section is located on the side of the engine. It is driven by the N2 rotor. The accessory section drives the electric generator, oil pump, fuel pumps, and hydraulic pump. Let's first look at the controls and indicators. The controls and indicators for the power plant are located on the aft overhead panel, forward overhead panel, center instrument panel, and control stand. The reverser lights, power management control or PMC switches and lights, and the low idle light are located on the aft overhead panel. The fuel valve closed and filter bypass lights are located on the forward overhead panel. The engine start switches are also located on the forward overhead panel. The engine instrument system is located on the center instrument panel. The reverse and forward thrust levers and start levers are located on the control stand. Now, let's discuss the engine fuel system. The indicators for the fuel system are located on the forward overhead panel and the center instrument panel. Each engine has a start lever on the control stand. Each lever has two positions, cutoff and idle. The engine fuel shutoff valve is operated by either the start lever or the engine fire warning switch. If the start lever is in cutoff or the engine fire warning switch is pulled, the engine fuel shutoff valve will be closed. When the engine fuel shutoff valve is closed, the fuel valve closed light will illuminate dim blue. When the start lever is raised to idle, the engine fuel shutoff valve opens. The fuel valve closed light illuminates bright blue while the valve is in transit and then extinguishes when the valve is open. Fuel from the tank flows through the engine fuel shutoff valve to the first stage fuel pump. The first stage fuel pump is powered through the accessory drive. Fuel is delivered under pressure to a fuel oil heat exchanger. The heat exchanger warms the fuel and cools the engine oil. The fuel then flows through a filter with bypass capabilities and is delivered to the second stage engine-driven fuel pump, where fuel pressure is increased for proper combustion. The fuel filter bypass light monitors the pressure differential across the bypass filter. When the pressure differential becomes too large, the light illuminates, indicating a contaminated fuel filter. Fuel leaves the second stage pump, which is also powered by the N2 rotor, and enters the main engine control. The main engine control meters the proper amount of fuel to the burner section for combustion. As the fuel leaves the second stage pump, A portion of the fuel is diverted through a second filter and then through the fuel heater. Hot engine oil is used to heat this portion of fuel before it is fed into the main engine control. This heated fuel keeps the main engine control free of ice buildup. The fuel leaves the main engine control through the main engine control fuel shutoff valve. The valve is opened by placing the start lever to idle. The rate of fuel flow is sensed as the fuel leaves the main engine control and is displayed on the fuel flow indicator. The digital display provides the rate of fuel consumption or the amount of fuel used since last reset in kilograms per hour. The fuel flow indication pointer always indicates the current rate of fuel flow in kilograms per hour. The digital display also shows the current rate of fuel flow, except when the fuel flow used switch or the fuel used reset switch is pushed. If the fuel flow used switch is pressed, the digital display will show the fuel used since the last reset for a period of 10 seconds and then revert to fuel flow rate. In this example, 1,800 kilograms have been used by each engine. When the fuel used reset switch is pressed, the computed fuel used will be reset to 0. The correct answer is B. The fuel heater operates continuously, supplying heated fuel to the main engine control. Next, let's discuss the engine oil system. The indications for the oil system are located on the center instrument panel. Oil is removed from the bearings and accessory gearbox by scavenge pumps. From the scavenge pumps, the oil flows through a scavenge filter. The scavenge filter has a bypass feature with pressure sensors at both the inlet and outlet. If the scavenge filter becomes contaminated, the amber oil filter bypass light illuminates, indicating an impending bypass of the scavenge filter. The oil temperature indicator monitors the temperature of the oil after it has left the engine. After the oil leaves the scavenge filter, it passes through the filter heater and fuel oil heat exchanger. The oil then returns to the oil tank mounted on the side of the engine. The oil quantity indicator displays the amount of usable oil in the tank in percentage of full tank quantity. The oil is drawn out of the tank and delivered to the engine by an oil pump. The pump is driven by the accessory section. The engine-driven pump produces oil pressure. The pressure output of the pump is monitored by a sensor downstream of the pump and is displayed on the oil pressure indicator. The output pressure of the oil pump is unregulated, which means the pressure varies with engine speed. This is indicated by the large green band on the indicator. At low power settings, as in descent, the oil pressure may drop to the yellow band. This is a normal pressure range for the CFM56 engine. However, if the oil pressure drops into the yellow band with takeoff power set, do not take off. A low oil pressure sensor is located downstream of the oil pump. If the oil pressure drops below the red line on the oil pressure indicator, the light will illuminate. After passing the low oil pressure sensor, oil is then delivered to the engine bearings and gearbox. Answer B is correct. The output pressure is unregulated and varies with engine speed. This is indicated by the large green band on the indicator. Now we will look at the engine instruments. The engine instrument system is located on the center instrument panel. The N1 indicator senses fan speed from a tachometer. N1 is the primary reference for setting and monitoring the thrust output of the engine. The N1 indicator displays actual N1 with a pointer and a corresponding digital readout. Target N1 is displayed by a reference bug. N1 manual set knobs are located in the lower left-hand and lower right-hand corners of the engine instrument system panel. With the knob pushed in, the reference bug is set by the FMC. The N1 manual set indication above the N1 indicator is blank, but the target N1 may be read on the FMC. When the N1 manual set knob is pulled out, target N1 can be set manually. Both the reference bug and the digital readout can be set. Located above the indicator is a red overspeed warning light. When N1 overspeed occurs, the light will illuminate and remain illuminated until the overspeed condition is corrected. The exhaust gas temperature, or EGT indicator, measures the temperature of the exhaust gases in the turbine section of the engine. The EGT indicator also has an over-temperature warning light that illuminates when maximum EGT is exceeded. When the EGT drops below the limit, the light will extinguish. The EGT indicator is part of the abnormal start advisory system. If an abnormal start is in progress, the digital display will flash. The N2 indicator measures the speed of the N2 compressor. The red overspeed warning light operates the same as the warning light on the N1 and EGT indicator. The correct answer is B. N1 is the primary reference used to set thrust. This completes the discussion of the primary engine instruments. Now let's examine the remaining engine instruments. Let's look at the engine vibration monitoring system. The engine vibration indicators are located on the engine instrument system panel below the oil system indications. Engine vibration is measured at the number 1 bearing. Any sudden or progressive change in the vibration level will be displayed and may be an indication of an engine malfunction. Now let's look at the Power Management Control, or PMC. The PMC controls and indicators are located on the aft overhead panel. The PMC is an electronic system with limited authority over the main engine control to adjust the amount of fuel going to the engine. The PMC uses thrust lever angle from the main engine control, fan inlet pressure, fan inlet temperature, and N1 RPM as inputs to make fuel flow adjustments to the main engine control. Let's look at PMC operation during a climb. When power is set for climb, the PMC will adjust the amount of fuel from the main engine control so the climb can be accomplished at a constant thrust, with no further changes in thrust lever position required. The PMC offers limited engine overspeed protection in the event the thrust levers are moved to the forward stop. When a PMC is operating properly, the white on indicator will be in view and the in-up light will be extinguished. Should the PMC fail, the PMC in-up light, the engine annunciator light, and the master caution light will illuminate. Next, let's look at engine idle speeds. A low idle light is located on the aft overhead panel. There are 2 engine idle speeds, high idle and low idle. Let's first look at high idle RPM. With the thrust levers at the idle position, the engines maintain at least high idle RPM, which is approximately 30% N1 whenever the airplane is airborne. On landing, the engines maintain high idle RPM until 4 seconds after touchdown. This provides quicker engine acceleration for reverse thrust. Now let's look at low idle RPM. Low idle RPM is used only for ground operations. Low idle RPM is approximately 22% N1. The low idle light illuminates in flight when one or both engines are operating below high idle RPM. The low idle light is accompanied by the master caution and engine annunciator lights. This completes the discussion of Power Plant Part 1. Continue with Part 2.